Okay, so we worked hard to get to this point where all we needed to do was we've got our approximate accumulation function graphed. All we need to do is slide the slider delta x, make delta x smaller. The step function gets closer and closer to the actual rate function, and the accumulation function approaches the true accumulation function. And when delta x is sufficiently small, really, really small, we've created the actual accumulation function. If I turn off the original rate function, look at the step function on the left. That's a step function. Those are constant rates, right? But delta x is so small, we can't tell the difference. We can't tell the difference. And therefore, we get an accumulation function where we can't tell the difference between approximate and exact. So that's the journey we've been on. So what we did, exact rate of change, approximate rate of change, approximate accumulation, exact accumulation. And we earned the rights, we did all the groundwork, we earned our dues, so we could go right from exact rate to exact accumulation. And now we want to go the other way. Okay, we're going the other way now. Starting with exact accumulation, working to exact rate. Okay, and again, we want to be able to do that, understand the nuts and bolts in between, but do it kind of in one step. All right, but the question is, where do we find exact accumulation functions? What is an exact accumulation function? Can you give me an example? Where is that? What is that? Where have we seen those before? Have we ever seen an exact accumulation function before? Can you give me an example? Steve, can you give me an example?
Tracking distance over time, or through time.
Okay, and so isn't that just a quantity function? So distance is just a quantity. How can we see it can we see distance as accumulation?
Yeah, as you go up, then you go further.
Yeah, so exactly. So any quantity function, all right, so any quantity function, for instance, area of a square, okay? It's a quantity function. You give it the side length, it gives you the area. But it can be thought of as accumulation if we let what? If we let the side of the square increase little by little, then that area builds up, right? The area builds up. So any quantity function can be thought of as an accumulation function. Okay, so therefore it can be written so we can write any quantity function as the integral of its rate. Right? All right, so same thing with the volume of a sphere, okay? Volume of a sphere is 4/3 pi x cubed, but it could also be written as an accumulation from 0 to x of whatever its rate function is. All right, so any function that gives an exact amount of one quantity as a function of another is an exact accumulation, and therefore can be represented as the integral of its exact rate of change function. We just don't know what the rate is, right? So we know how to calculate volumes of a sphere, 4/3 pi x cubed, pi r cubed. If we want to write it as an accumulation function, then we need to know its rate. We need to know its rate of change function. Okay, so that's our goal here. So this is the whole point. Given the accumulation, what's the rate of change? Given the accumulation, what's the rate of change? Okay, so in order to do this, we said there's some tool. We have a lot of tools from our forward journey, okay? Rate to accumulation. We have a lot of tools that we're going to use for this reverse journey, but there's some new tools that we need. One of those is average rate of change. Okay, and we started talking about that last time with this. So one of these tools that we need is average rate of change, and we started by talking about speed. And we looked at Usain Bolt, and it's Emma's birthday today. She's won today. And she's as fast as ever. Okay, and she's a lot happier than that. Okay, so what did this have to do with, so we're talking about Usain and his average speed running his world record race. And how did we define his average speed? What was the average speed of Usain running the race? Chloe?
It's a constant rate to go the same distance in the same amount of time.
Okay, so what does Emma have to do with that?
Emma is the average speed. Like Emma's going the average speed the same.
She said Emma's going the average speed of Usain, right? She's going the constant rate to get the same distance in the same time as Usain. So she's running his average speed, because average speed is what? The constant speed to go the same distance in the same time. So now we want to extend this. We don't want to be able to do this just with speed and distance, but we need to talk about average rate of change of any quantity, right? So given any two quantities that change together, how can we define average rate of change? So if average speed is the constant speed needed to cover the same distance in the same amount of time, then what is, just more generally, what is average rate of change? So we started this bar glass example, and I worked hard over the weekend, over my break for you. Okay, this is all built with a graphing calculator. And so, what do we got? So we can fill up the glass here. We're going to put volume now. Maybe. Oh, the other one's got to be turned off. Okay? So volume of water is our independent variable on the x-axis. And these typical glasses hold about 14 ounces. And as you fill up the volume, so at 14 ounces, in my glass, it's just over 5 inches tall of height. So we got quantities of height of the water and volume of the water. So when this glass is all the way filled up, right there. And then we talked about what the graph looks like. So what will the graph look like for height versus volume? So take a second to review. What will that graph look like if we graphed height as a function of volume?
That's not.
Is that what you thought? That's it, okay? So now, let's calculate for filling up the whole glass. So from 0 to 14 ounces, what's the average rate of change? And so I'm showing you the height right here, 5.05. The current value of height is 5.052 inches when you hit 14. When you hit 14 ounces of water in the glass. So find the average rate of change of height with respect to volume. Go, find the average rate of change of height with respect to volume.
Yeah, that's not X is volume. I got 0.36.
Okay, Jamal, can you do it?
Ounce water. Just divide it. It's constant.
What's that? 14 over 5. 0.05. What do you think? Molly, you agree with that?
Yeah.
So we want 14 divided by 5.052. You disagree?
Sorry. 5.
You went the other way. Which is the average rate of change of height with respect to volume?
Second one.
You want to change?
Yeah.
You can change, okay? Do we get a number? What is it?
0.36.
Inches per ounce. Okay, now, so this is the average rate of change. Who can interpret that number? What does that number mean relative to this glass. What does that number mean relative to this glass? So, as a hint, remember Emma. Okay, remember Emma, and you're saying it's the same thing, but now it's just not speed anymore. We're talking about the change in height per volume. What would that number represent? 0.361. Right.
Is it the constant height with respect to 1 ounce
Okay.
of fluid?
So it's a constant rate of change. Okay. So what constant rate of change is it?
0.361. I don't know.
Yeah. So right. Good. So that's the main thing. That's a constant rate. We want to be really specific. What constant rate is it, Nicholas?
It's the constant rate needed to fill a 14-ounce glass in the same amount of time as the changing rate.
Okay. So be careful because time isn't. We're not looking at time here.
I am.
Not looking at time at all. We can change the volume however we want, and we get a height. So it's not. So I can take some out. Take some out. Look at that volume. Look at this volume. So it's not. It's really not about time. What does this number mean? 0.361 inches per ounce. Peter.
If we were to fill a glass that was straight along the sides of paper, it would take the same amount of water to fill that volume over that amount of volume.
Okay. Anybody? So got some good there, Ross.
It's the amount, or it's the rate of change for the volume needed to reach that height, or to reach the same height using the same amount.
So it's the constant rate of change that would
Reach the same
reach the same height
using the same amount.
using the same amount of volume. It's the constant rate of change that would reach the same height or change in output for the same change in input or same change in volume. And so you talked about, it was Peter, so how can we represent that?
With a straight edge glass instead of a paper.
Okay, and what about the graph of the constant rate? Can you imagine what the graph will look like of the constant rate? From where to where? Is that what you're imagining? And we can do it as, right? So notice how the heights, so you can take a minute, talk about the heights of the, as we increase the volume. Talk about the heights of the water in the two glasses and how that is reflecting how the actual height versus the constant rate height is accumulated. So go. So what's happening? So look at these heights of the water and compare that to what you're seeing in the graph. Go.
The constant rate is like
Okay, Chris.
The rate of change of the accumulation of the first one.
Okay.
That's the. I know what to say. I just don't know.
Okay.
The second one is constant because it's just following the cup, and the cup size doesn't change.
Right.
And then the other one, it gets bigger at the top, so it takes longer to fill that up than at the bottom.
Okay. Other analysis. Yeah, Shannon.
Well, it's not about time, so when it gets to the top, it's like wider, so the height doesn't fill up as much. With the same amount.
Okay. So why does the height go more quickly for the actual glass at first?
Because it's narrower.
Yeah, because it's narrower. So in the first half of the glass, it's narrower. It's gonna per volume, the height is gonna increase more per volume. And then what happens in the second half of the glass?
It's wider.
It's wider. So then the constant rate right, we'll catch back up. And so how do we see that in the graphs?
The blue graph is starting to level off.
Right? Yeah, so we get a faster rate at first, and then a slower rate later. And so that they reach this, but here's the key. Same height for the same amount of water. So what is the average rate of change? It's the constant rate of change, right? It's the constant rate of change. Which constant rate is it? Yields the same change in height. In this case, 5.052. For what? For the given, whatever the given change in volume is. So the average rate of change is the constant rate that yields the same change in height for the given change in volume. So memorize that. And practice. So yeah, we're going for understanding, but at first you got to memorize that. Memorize it and say it over and over again and think about it every time. It's the average rate of change, the constant rate that yields the same change in height for the given change in volume. In this case, 0.361 inches per ounce. Okay, so now what about this? I'm going to pick a different change in volume now. I want to pick the change in volume from 1 to 6. So starting at 1 ounce. And ending at 6 ounces. So I'm representing that on the x-axis as this purple change in volume from 1 to 6. Okay, find the average rate of change from 1 to 6. I'll give you some numbers here. So I want you to find the average rate of change from 1 to 6. There's our height. At 14 ounces again, it's 5.052. So at 1, the height is 0.543. 0.543 inches at 1 ounce. And at 6, 2.66. So at 1 ounce, the height was 0.543, is that right? And it's 6 ounces, 2.66. So our change in volume is 5. Going from 1 to 6. Find the average rate of change of water to volume. Interpret the meaning of this value. And if you make a sketch on your own, add appropriate elements to your sketch, to illustration, to represent the changes and the average rate of change. Okay? So once you have the number, talk it through with the person next to you. What does the average rate of change mean? What does the average rate of change mean? Go.
That's
Oh, I got it.
I just did Delta Y equals K Delta X.
Yeah, I got it.
I see Delta. Oh, I just said yeah. Oh, it's 6. And then
Okay, what did you get? So Linwin, did you get a number for the average rate of change? 0.423. Did you get 0.423? Ish. Okay, good. All right, what does it mean? Gilbert, can you interpret that number? 0.423 is what?
That is the average rate of change of the volume of the cup as the ounces increase.
Okay. So then what is that? What is the average rate of change, Zoe?
That would be the amount of inches that the glass would, constant rate of change of the amount of inches for the same amount of volume.
Okay. Did you hear what she said? Brent, you want to give it a try? Okay, well, so you say it yourself. What does this mean as average rate of change is
4.3,
0.423?
1 and 6, for that like changing rate.
Okay.
To get the same volume in 6 seconds, or 6 ounces. To get the same height of 6 ounces, we have to go up by 0.423 inches an ounce.
Okay. So he's saying to get the same increase in height as the actual glass, going from 1 to 6, you have to increase 0.423 inches per ounce. Is that what you said? What do you think? Good? And what would that look like? So this is what this would look like. Okay.
We'll say like if you drew a line from whatever the value of 1 on the blue graph,
Okay.
the value of 6, or the value of the line at 6 on the blue graph, a straight line between 2 points.
Like this?
Yes.
Right. Okay. So that purple line represents the average rate of change is 0.423 inches per ounce. What? Would result, it's the constant rate of change that results in the same change in height as the actual glass when filled from 1 ounce to 6 ounces. It's the constant rate of change that will result in the same change in height as the actual glass when filled from 1 to 6 ounces. Okay, so we talked about let's look at the other constant rate, greater or less for the whole glass, comparing those two. So is our new rate of change greater or less than the average rate of change for filling the whole glass?
Greater.
Greater. Okay, because for the same change in volume, we're getting more of a change in height. You see that? We're getting more of a change in height for the same change in volume as a constant rate. So for the new average rate for this from 1 to 6 ounces, can we use this bottle to represent that new average rate for all these? So what would the new bottle look like? So from here to here?
No, on the other glass.
What's that?
The other one.
So I want to represent this new average rate of change as a different bottle. Can I use this one?
I
Don't think so. I think you're right. Ross?
It has to be narrower.
He wants narrower.
Because you're going to see a taller accumulation every time you have. Right?
Yeah, that's right. You need a narrower glass now to represent this new average rate from the height of whatever the change in height was. Because we're seeing a greater change in height per change in volume. Now compare the two, as we go through this from 1 to 6 ounces, compare the two changes in height, compare the two heights of these two glasses, the actual glass and our fictitious glass. How do they compare? What do you see? How do those two heights compare for this 1 to 6 ounces? What's that?
It's closer.
They're close, right? They're close. And what are we talking about doing? We're talking about starting with actual accumulation and moving towards actual rate. What would the first step in that reverse process be?
The approximate
Approximate what?
rate?
Approximate rate?
No.
Approximate accumulation. So do you see how we're going to use average rate of change to be a constant rate of change that's approximating our actual accumulation? You see? This is the backwards journey. I saw Melody first and Kevin.
In essence, are you saying we're kind of building it piecewise out of this?
So we've got this actual accumulation. We're going to build piecewise out of what?
Out of the blue line?
Right, so the blue ones are actual accumulation, and we're going to build a piecewise, approximate piecewise accumulation function out of average rates.
I just don't understand the pink cylinder.
Yeah.
Like, why is it smaller? I don't understand. Like, why isn't it just the same?
Why isn't it just the same?
Yeah.
Get back to this. Because the new average rate, look at the old average rate, that's the red one. And look at the new average rate, just from ounces 1 to 6 ounces. For the same change in volume, we get more of a change in height for this part of the glass than we do for the whole glass. You see? So the same change in volume, you're getting a bigger change in height. So that means you need a narrower glass to get, for the same change in volume, to get more height, you need a narrower glass. Yeah, see? Yeah. Okay, let's see what I want to show you is that, so now we've got this average rate that's doing a pretty good job of mimicking the actual accumulation of height. It's doing a pretty good job. And so this is our first step in the reverse process. We start with exact accumulation. We're going to use average rates of change to build approximate accumulation. And even, look how wide this is, 5 ounces difference, but yet it's still doing a pretty good job of matching the height. Okay. But this is the key. What is average rate? So memorize this. The constant rate of change that would result in the same change in output for the given change in input. Constant rate of average rate is the constant rate that would result in the same change of output for the given change in input. Memorize it. Any questions?
If you wanted to say the average rate of change generically, like not with respect to time or ounces in this case, how would you say it? Like over a delta x interval or something like that?
Yeah, so talk about input and output. So that's good. So what if you have a function with some input and some output, you pick a specified interval of input, what is the constant, what is the average rate of change over that interval of input? Marco, can you do it? Anybody? So for any function with some input and output, we've got a specified interval of input. What's the average rate of change over that specified interval of input? See if you can talk it out. It's the same thing again. Now we're totally general. See if you can talk it out. So given a function and a specified interval of input, what's the average rate of change over that interval of input? Go.
The constant rate is the change in y.
I'm just trying to explain
Some change
in terms of y and x.
y is
Who thinks they can do it? Somebody new. Someone we haven't heard from yet. Janae, can you do it? Given a function and a specified interval of input, the average rate of change over this interval is, who can do it? Can you finish it? Janae.
It's an approximation of the change.
It gives an approximation of the change, of the changing rate. Christian.
I mean, I don't know about this. I don't know if I can articulate it exactly how I think you want it, but I was thinking about doing it as the change in y over the change in x, like the interval.
That's how you calculate it, that's true. But what is it?
Is a constant rate of change.
Yes, the constant rate of change. Want to keep going, Alexander? Which constant rate of change is it?
Over the specified interval.
Okay, it's the constant rate over the specified interval. Jonathan? That yields the same change in output as what? As the function over the same interval of input. Does it make sense? Memorize it. Memorize it. That's what average rate is. We're going to use average rate now to build our approximate accumulation function. Because look, it's doing a pretty good job. You can barely see any daylight in there. See that? You can barely see any daylight between that average rate and the actual function. And the heights were matched up pretty good. Okay, see you Friday. Check Blackboard for homework.
Question, I get 89.7. Is that my final is 90 or 89?
89.7.
Oh, okay, thank you.
It's virtually the same as a 90, yeah.
On my test,